The Bernoulli principle was discovered by Daniel Bernoulli in the 18th century during the Age of Enlightenment and was part of the scientific revolution. Daniel Bernoulli was born in Groningen, Netherlands on the 8th of February, 1700. He was a part of a family of mathematicians. Daniel's father, John, thought that the job of a mathematician was underpaid and did not wish for him to pursue that line of work. John persuaded Daniel to become a doctor and agreed to teach Daniel mathematics privately. Because Daniel was pushed to be a doctor but wanted to be a mathematician himself, he became a very well-rounded scientist and mathematician. He made many great achievements in his lifetime in many different fields of science and math, chiefly the publication of the book Hydrodynamica, in which Bernoulli's principle was introduced. Unfortunately, Daniel's father was a very jealous man. John and Daniel had accidentally entered the same contest and then received a joint victory. John was incredibly angered to find his son considered his equal. After this incident, John banned his son from his home and the relationship never mended. In an effort to discredit Daniel, John published his own book, Hydraulica, which took credit for many of the discoveries Daniel had written about in his book. Daniel later tried to build a better relationship with his father, but John was not interested. The Bernoulli principle simply states that as a fluid's speed increases, that its pressure decreases, or vice versa, as a fluid's speed decreases, its pressure increases. There are many ways to illustrate this effect. Many museums have this simple setup showing the Bernoulli principle. The ball floats in the air because it is inside of the fast-moving column of air. The fast air has a lower pressure than the air around it based on the Bernoulli principle. The high-pressure air outside of the column of air pushes on the ball from all sides, keeping it in place. The fast-moving air pushes up on the ball, counteracting the force of gravity. In my experiment, I used a leaf blower to create a column of air. I then placed a tennis ball in the fast-moving air. I slowed down the video to show the movement of the ball in the column of air, in the column of fast-moving air. As you can see, the higher pressure air around the column of fast-moving air prevents the ball from falling off the fast, low-pressure column of air. This experiment is a great demonstration of the Bernoulli principle, but let's see some experiments that are more relatable to everyday life. This first experiment shows high-speed air, a leaf blower blowing over the top of a roll of toilet paper. Based on the Bernoulli effect, the high-speed air creates an area of low pressure, drawing the toilet paper up and off the roll. This causes the roll to quickly unravel. Let's see that in slow motion. As you can see from this slow video, the toilet paper is drawn up and travels with the fast-moving air until it drops. This drop is where the air is no longer moving as quickly because the leaf blower's range is only so long. This definitely shows the Bernoulli principle, but unless you are trying to TP someone's house, how is it applicable to everyday life? This experiment demonstrates how the Bernoulli principle affects lift. How does an airplane fly? The answer lies with lift. To understand lift, it has to be understood that just like how heat travels to cooler objects, high-pressure fluid typically travels to low-pressure fluid. An airplane's wings are flat on the bottom and curved along the top, causing air traveling on the top of the wing to have to travel a greater distance than the air traveling below the wing. This causes the air on top to move faster than the air below. Based on the Bernoulli principle, the faster air on the top of the wing creates lower pressure than the slower air on the bottom of the wing. This causes the airplane to be drawn up as the two different pressures try to equalize, thus creating lift. Just like the toilet paper experiment, where the fast-moving air on the top of the toilet paper draws the paper up, with the fast air, the air over an airplane's wing draws the wing up, creating lift. Believe it or not, a sailboat also uses lift to move. However, with a sailboat, the lift is not drawing the boat up, but to the side. A sailboat's sail works exactly the same way as an airplane's wing, except instead of being parallel to the ground, a sail is perpendicular to the water. This lift allows a sailboat to move not only with the wind, but at an angle to the direction of the wind. This is why a sailboat can move in almost any direction except straight into the wind. Another example of the Bernoulli principle can be found in almost any home. A chimney. When a fire is lit in the fireplace, why doesn't the smoke flow into the house? Above the chimney, the wind has to move quickly to get around the chimney, thus creating low-pressure air. In the chimney, the air is not moving as quickly, so that air is a higher pressure than the air outside the chimney. The air with the smoke in it is drawn outside to the air that has lower pressure. Let's look at an experiment of this happening. As you see the scaled-down chimney, the cup is the actual chimney, the bits of paper are the smoke, and the hairdryer is creating the rushing air. The low pressure above the cup drew the paper up and out of the cup, just like smoke is drawn up and out of the chimney in a house. This experiment does not work quite as well as a real chimney does, as smoke already goes up to an extent because hot air rises in general. My last demonstration of the Bernoulli principle shows how the Bernoulli principle affects fluids other than air. In this experiment, I will use a straw to build a small contraption that will be capable of drawing water up while someone blows out. First, I will take a thin drinking straw and cut the flexible portion off. I will then cut a third of the remaining straw off. Next, I take the longest piece of straw and bend it in half. I then cut a V-shaped wedge into the long piece of straw. Lastly, I insert the short straw into the hole created by the wedge. I placed the bottom of the short straw into a small glass of water. I dyed the water blue so that the spray could be clearly seen. I had my brother blow into the end of the T-shaped contraption. As he blew, a column of fast-moving, low-pressure air shot through the top of the tube. While this low-pressure air went through the tube, the higher air pressure pushing down on the water forced water up the shaft and into the fast-moving air. A small amount of water is carried out of the straw mechanism and sprays onto the sheet of paper. The spraying is caused because as soon as the water droplets reach the low-pressure air, it slows down the air and raises the pressure. This is why the water is sprayed and does not just stream out. Once the water droplet exits the straw contraption, the air speeds back up because it is no longer blocked. This again causes the air pressure to drop and the water is again forced up the straw. This use of the Bernoulli principle can be found in garden sprayers, perfume bottles, and fertilizing equipment. Even though Daniel Bernoulli published his discovery of the now called Bernoulli effect hundreds of years ago, his principle is still used by engineers today. From creating an easy way to fertilize a garden, to explaining why chimney smoke doesn't flood into homes, to finding a way to keep a 1 million pound airplane from plummeting to Earth, the Bernoulli principle is used for each one.